First of all, thank you very much to the organizer for setting up this nice conference and program and for the kind invitation to speak here. So I will tell you, in a sense, continue the previous talk, but this time more from a numerical perspective on various Monte Carlo studies of critical behavior in the presence of surfaces or defects. And now we have seen that there are many. This is a work partially in collaboration with Max and his student Abhijit Krishan. We have seen there are many interesting phenomena appearing when we have a system in the presence of boundaries, and there's been a lot of developments, but in particular, even the problem of classical models in the presence of boundaries has experienced a renewed interest in the past years, which from one side came from the new developments in the field theory and also in the conformal field theory. From my perspective, I was interested in going back to the standard old problem of surface critical phenomena from the discovery that there is a series of quantum spin models that undergoes a quantum phase transition in the standard classical or 3 universality class. And then it was found that in some cases their boundary exponent was completely unexpected. And I will maybe say a few words more about that. And this also motivated me to go back to the standard classical surface critical behavior to see if things were completely understood. And most of the work I represent here is based on Monte Carlo simulations of various models. Now, I'll be very quick, since we have already heard in the previous talk a nice introduction of the various model and phases. Generically, if I say I have a model in 3 dimensions with a 2-dimensional surface, and I'll take one of the classical ON standard model, you can study without losing generality the phase diagram and the phase transition just by considering 2 coupling constants, one coupling constant deep in the bulk and one coupling constant on the surface. So, for example, the case of the Ising model is very well understood. Depending on the various surface coupling constants, you can have a surface transition where the surface orders in the presence of a disordered bulk. And on the critical bulk line, you have this 3 phases: the ordinary universality class, the special, which is an unstable fixed point, and the extraordinary universality class, which essentially is when the bulk becomes critical in the presence of an ordered surface. Now, things start to be interesting and have led to unexpected discoveries when you consider the ON models for n equal 2. And we have heard in the previous talk that on this, we have a similar phase diagram qualitatively, but there is the surface transition is a KT transition. And we heard also in the previous talk that there is a new phase. It's called the extraordinary log phase, which happens exactly when the bulk is critical and we have a sufficiently strong surface interaction. And this extraordinary log phase is characterized by a 2-point function that decays very slowly, so it's almost ordered, the model, but not quite. And this has been also verified by some recent Monte Carlo simulation. And even more interesting is the case when n is larger than 2, because in this case the surface transition does not exist. But a priori, it is not excluded that there could be still a surface transition when the bulk is critical. And indeed, this is the case. We still have a transition to the extraordinary log phase, which I also studied a few years ago in detail for the case n equals 3. And this picture, this phase diagram, persists up to some critical value of the number of components. A similar picture is also found when you consider a plane defect. In this case, okay, for n equals 2, you have the transition, and the only important difference with the previous case is that the special universality class, in a sense, is trivial because it corresponds to a plane where the coupling constants are exactly equal to the bulk one. So the special universality class has exactly the same exponent of the bulk ones. But apart from that, the phase diagram is qualitatively similar, except that now the extraordinary log phase survives for any value of n. So I have studied a series of, we have studied a series of this physics by Monte Carlo simulations. And what the first thing you have to ask which Hamiltonian I have used. So to study many of these models, I just used a lattice model in the ON universality class. But instead of using the standard ON models, I used the 5 to the 4 lattice model, which has an important technical advantage. If you look at the Hamiltonian of the model, you can still specify a coupling constant for the boundaries and for the bulk. The phi is a vector of n component, but whose length is not fixed to 1, unlike the standard hard spin model. And the Hamiltonian contains an additional parameter, this lambda parameter of the local potential felt by the field. And this model has been studied a lot in the past decades. It's known, the critical lines are known. And in particular, and that's the technical advantage, it is possible to fix one value of lambda such that the critical behavior at a given critical temperature as a function at this lambda star, one model, the leading scaling correction are suppressed. So that means that we have a better scaling control, and this is particularly useful when you study boundaries or defects where the presence of this boundary gives rise to additional new scaling correction. Now, I would say, fortunately, these models have been studied a lot in the literature, and we know the value of the lambda star for 2, 3, actually also for n equal 4. We also know the position of the critical points. So in this sense, the bulk is absolutely very well under control. And so that's why you can concentrate only on the surface or defect critical behavior by tuning the coupling constant on the surface in the case of open boundary condition, or on a plane defect in the case of this other geometry. And the first case I will present you is the case n equal 3. So this is the O3 model where we don't have a phase transition when the surface is alone, but next to a bulk, as you see in a moment, we have now evidence that there is indeed a surface transition. And so all you have to do is to set, so study the model for n equal 3, as I said, the critical parameter are known, and one then scans the surface quantity as a function of the boundary coupling. Now, one canonical way to study phase transition is to use the renormalization group invariant quantities. And in particular, you can study the famous Binder ratio constructed from the boundary magnetization, and as a function of the coupling constant on the surface. And a crossing indicates usually a phase transition. If you look, this is a picture on a big scale, you see that, well, there is a crossing. However, when you zoom in, you will see that the crossing slightly moves. So the question then remains whether this move converges to a true critical point, or if it is we are seeing just a long crossover, slow crossover behavior. And to answer this question, we have to systematically increase the sizes, but also particularly the numerical precision. So this is a zoom over the previous picture where I have systematically increased the lattice sizes, and in particular, it is necessary to increase a lot the numerical precision in order to be able to single out the crossings, indicating a surface phase transition. And the reason why you need a high precision, you can see from the Y scale, which is very small, is the fact that the slope of this curve are growing as a function of L very, very slowly. Now, without entering too much in the technical detail, to answer the question, do we have phase transition, which are the boundary exponents, you have to do a Fanaster scaling analysis. You exploit the usual Fanaster scaling answers where an RG invariant quantity has this scaling behavior. And by a proper analysis, you find that, yes, there is a transition. It's a normal transition, so it doesn't have some unusual scaling properties. However, what is unusual is the fact that the relevant exponent here is very small. And that also explains why the slope, which is proportional to L to the power of this relevant exponent, grows very, very slowly as a function of L. Moreover, you can also compute the magnetic exponent on the boundary at this transition, and you find that there is a characteristic exponent which is completely different from the ordinary one. And what is interesting to observe is that I very, very briefly mentioned that there are a series of quantum spin models which have shown on the boundary unexpected boundary exponent. However, their bulk properties belong to the classical O3 universality class. And the exponent, the unexpected exponent, which are sometimes measured, are numerically close to this value. And so while I think that probably the question is not yet settled completely, one possibility is that this model map, they are accidentally close to the spatial transition. And of course, the spatial is an unstable fixed point, so you generally need a fine-tune of the parameter. But one ingredient that could make this picture possible is the fact that the relevant exponent is very small. So there is comparatively a large, possibly large crossover region where you observe exponents which are close to the spatial one, even if you are not right at the spatial universality class. Okay, but anyway, we have studied the spatial transition. We have established that there is a spatial transition on the boundary on the n equal 3 model. And if there is a spatial transition, there must be also another phase for larger value of beta, the extraordinary phase. And this extraordinary phase, it turns out, is this new extraordinary log universality class, which is, as we have heard also in the previous talk, closely related to the so-called normal universality class. So what is the normal universality class? It's simply the class, the surface class that you obtain by putting a surface field. When you put a surface field, you immediately order the surface. And now you say, maybe, why is it called normal? No? I think that it traced back to a paper by Michael Fischer, which says, talking about this situation where you have an Ising-like model in the presence of a surface field. It says, which, however, in the laboratory is more normal than the ordinary transition. So this is why it's the normal universality class. Why is it so? No? The reason is the following. You can experimentally realize this physics in the Ising case by considering a fluid, for example, a binary liquid mixtures, which under certain condition undergoes a mixing-demixing transition, which can be continuous, and then it belongs to the Ising universality class. And the order parameter is up to a constant, the concentration of one of the two species of the mixtures. So here, for example, is a snapshot of this mixing transition from the group of Clemens-Beckinger. Now, whenever you expose this mixture to a boundary, it could be a plane, it could be a substrate, it could be the surface of a colloidal particles, generically the surface prefers to absorb one of the components. Which one depends on the chemical structure, but typically this is the case. And the local preference of absorption on boundaries can be modeled by, since the order parameter is the concentration of the species, can be modeled by a surface field. So this is why this is the normal case in the laboratory. Now, in the Ising case, the extraordinary universality class and the normal universality class are equivalent. So it doesn't matter whether the symmetry is broken explicitly or spontaneously. One can show in a fairly rigorous manner that the two surface universality classes are the same. For ON larger than 1, n larger than 1, we have instead a more rich picture. First of all, we break, by introducing a surface field, you break the symmetry ON to ON minus 1. So accordingly, you have to distinguish the modes of the order parameter parallel or orthogonal to the surface field. And they have a very distinct decay of the two-point function, different critical exponent. The longitudinal modes have an exponent 6, and the correlation of the transverse mode have a different exponent 4. And this can be directly related to the low-lying part of the spectrum at the normal universality class, because there are two operators which have a protected scaling dimension. One is a scalar under ON minus 1, and it's called the displacement operator, and has a dimension 3. And the other one is the tilt operator, which is instead a vector and has a dimension 2. Now, if you study any lattice model in the normal universality class, all you can say just by guided by symmetry is that if I take the component of the order parameter parallel to the surface field, this at criticality will be expanded into a combination of all the possible scaling fields, which have the same symmetry. So there are scalars under the remaining ON minus 1 symmetry. And vice versa, if you take the component orthogonal to the surface field, this will expand in all the other surface scaling vectors scaling field. Now the fact that the exponent that we observe on the lattice for the correlation longitudinal or transverse match exactly the scaling dimension of the displacement and the tilt operator means that these two are the low-lying operator on the theory. There are no other scaling field with a smaller dimension. So now the scaling, the dimension, the spectrum is known well. There's nothing particularly new to study. What is not known exactly are the operator product expansion coefficient that you obtain when you collapse the bulk field next to the surface. Now the bulk has an ON symmetry, but since the symmetry on the surface is broken, you have to consider two channels. And the component of the bulk, which is parallel to the external field, will allow the boundary operator product expansion, which contains all the scalars, in particular the identity and the displacement, whereas if you take the component orthogonal to the surface field, will expand in all the ON-1 vector on the surface, and the leading one we have seen is the tilt one. Now, these two, once you have introduced a proper normalization, these two coefficients in front are the universal boundary or OP coefficient. And so these are already per se interesting CFT data, which I think they were never calculated before. But the main interest in computing this number is that the theory predicts that out of these two numbers you build a universal combination alpha. And this alpha tells you the fate of the extraordinary log phase when you have a model without a surface field. So if alpha is positive, and we have two different formulas where you have an open boundary condition or a plane defect, then you have the extraordinary log phase. And in particular, the alpha parameter is strictly related to the power q, which is happening in the two-point function. And for the plane defect, alpha is always positive, so you always have the extraordinary log phase, whereas for the surface case, the alpha can also change sign, and then you lose the extraordinary log phase. Now motivated by this, we have studied the normal universality class. Again, I will use my preferred improved lattice model. At this time, I will also add a surface field to realize the normal universality class. So you have to distinguish the modes, which are the components of the order parameter, which are orthogonal or parallel to the surface field. And the goal here is to get the operator product expansion coefficient. So now, again, this can be arbitrarily technically involved. So we'll give you just the main ingredient, how you extract these coefficients. So the first ingredient you need is a dictionary between the lattice and the underlying CFT, and how the lattice operators, the lattice field, expand in terms of the underlying CFT fields. And you can see just by guided by symmetry that the bulk field will be contains all the vector ON vector for the bulk universality class. In particular, will be proportional to the order parameter field plus possibly other subleading fields. And on the surface, you have to distinguish the component parallel or orthogonal to the external field. And again, one will expand, containing the expansion, the displacement operator, and so on. And the other one will contain the ON-1 vector, will contain the tilt operator and possibly other subleading corrections. How do you fix this normalization constant? These are model dependent, and they are fixed by assuming that the two-point function of the underlying CFT fields are normalized in a way that the amplitude of the two-point function is exactly 1. So that's the standard normalization for CFT fields, done by computing the two-point function in the bulk or on the surface on the lattice model, and using this assumption here, you are able to extract this normalization constant. So now you have a dictionary between the lattice and the CFT. How do you extract the boundary of PE? So we start by the expression of the boundary operator product expansion. If you take the expectation value on the first line, you get on the left-hand side the value of the order parameter as a function of the distance from the surface, and on the right-hand side the expected decay with a known critical exponent, and the amplitude is this universal boundary operator product expansion. If you take the expectation value of the second one, you get 0 equals 0, because this is an ON-1 vector, but you can take the product with the tilt operator, and you get on the left-hand side the two-point function, 1 point on the surface and 1 point in the bulk, as a function of the distance from the surface. This will decay with a known exponent that you can also guess by scaling configuration. And apart from a numerical factor, the amplitude in front is the desired OPE. The second ingredient is that, well, we now know this 2-point function, 1-point function, and their prediction from CFT, we can link this to the lattice models by using this normalization constant, and including also a series of scaling corrections, which are important to be able to get a robust, precise result. You find that the 1-point function of the order parameter decays with some power, and the normalization in front times the universal OPE coefficient. And same goes for the 2-point function surface bulk, so 1 point on the bulk and 1 point on the surface. And here there are a series of scaling corrections. In particular, there are corrections which decays like z to -1, which are due to the presence of the surface, and they can always be encoded by shifting z in z plus a constant. And there are, of course, also finite size corrections, so the presence of the fact that we really have a finite size, we do have a second surface, so we have some correction, which fortunately the exponent of the leading one is known. Now this looks like a very complicated ansatz with many parameters, but what I want to point out is that basically we are fitting mostly the amplitude, because these critical exponents are known, are with a very high accuracy, and we use them as an input. And as well as also the correction to term, which also have a known corrections to scaling. And at this point is also where it comes, appears useful to having chosen an improved model, because if you have this correction z to -1, but if you didn't have an improved model, you also have a correction coming from the lowest irrelevant fields on the bulk, which has an exponent close to 1, so it's 0.8. So then, okay, this additional correction will be more difficult to disentangle with the correction coming from the surface. Anyway, yeah?
What is D?
D is the displacement operator, so it's the lowest scalar on the boundary, as a dimension 3. All right. So then, by doing a suitable fits of this quantity, you are able to extract the 2 universal OPE. Here's a comparison with a concurrent study, which used the conformal bootstrap. So there are 2 versions. There's the rigorous conformal bootstrap, which is able to exclude some part of the phase space of the parameters, and at the moment it's not able to constrain very strongly the value of the 2 OPE coefficient, but as you can see here by the zooming, the Monte Carlo results are perfectly in agreement with the rigorous bounds. There is also another version of the conformal bootstrap, which is the truncated conformal bootstrap, which does a reasonably good job in finding the OPE coefficient, but it introduces also a systematic small error. So that's why you see that the 2 numbers are not in full agreement. So here is a table of results for 2, 3, and 4, and out of the 2 coefficients of the boundary operator product expansion coefficient, we can extract the value of alpha. And the value of alpha for the open boundary condition or for the plane defect. And I'm not aware of other numerical determination apart from the truncated conformal bootstrap, which seems to slightly overshoot the Monte Carlo results. All right, so we have computed the OPE coefficient of the normal universality class. We have a prediction based on that, on the alpha universal parameter of the extraordinary log surface universality class. So where does this alpha enter? So, I will refer that Max did a more throughout discussion of this. Essentially, the alpha parameter is the first term in the expansion of the beta function of the parameter g that controls the behavior on the boundary, and it's essentially a linear sigma model coupled to the bulk. This alpha enters in the behavior of the 2-point function, this exponent q, which is related to alpha by this expression. But there is also another series of observables where alpha gives a more striking behavior, where alpha enters really in a much clearer way. And this is the finite size scaling quantities. So there are a series of finite size scaling quantities which are of common use in critical phenomena. For example, the ratio of the correlation length over L, correlation length computed on the surface, the spin stiffness, properly normalized such that it is RG invariant, the Binder ratio, and so on. which at the extraordinary log, as a consequence of the logarithmic flow of G to 0, display a logarithmic behavior as a function of L. And in particular, that's very striking that psi over L and the stiffness, they grow logarithmically in L. Now, that's a very, very peculiar feature of the extraordinary log phase. I would say that it's really a smoking gun feature, because usually if you just study a standard critical point, all this quantity, they just go to some constant, some universal constant. And here instead we have this logarithmic violation of the standard finite set scaling. The Binder ratio also approaches 1, but logarithmically slow, such that you can also build a combination of psi over L and U4, and this combination for large L converges to a sort of super universal number. So apart from this N, the alpha now has really disappeared in this number. So this gives us also a very clear prediction that one can verify on the extraordinary log phase. This is some Monte Carlo results for surface for open boundaries, where I tune my surface coupling strong enough to be in the extraordinary log phase. And you see that is clearly a psi over L, and also the stiffness shows a very clear linear behavior in the log of L. You can also try to do more. You can also try out of this linear behavior to extract the alpha parameter. And you find values which are in reasonably good agreement. Maybe they're slightly below the one that you would expect coming from the normal universality class. But I will tell you in a moment that there are some corrections, and we have also understood where this correction comes from. Same goes for plane defect. We have also studied a series of temperature invest coupling constant in the extraordinary log phase for n equal 2, 3, and 4. And again, you can see that there is a linear behavior. You can fit the value of alpha from the linear behavior, and it matches relatively close to the normal universality class. Maybe with, it is slightly smaller than that. Okay? And I will tell you now in a moment why it's slightly smaller. Same also goes for the a combination of G invariant, which in theory tells you that it should converge to a super universal number divided by n minus 1. You see here that for all the various geometry and values of n, this the dotted line is the expected limiting behavior. You see that for few values of the coupling constant as a function value slowly converge to the expected asymptotic value. So that's already quite a well, sorry, this B? It's a result. It's a result of the theory. So it's not. It's a number that you can compute numerically. It comes from the. So you use this term here, this expansion of Xaver L, and U4 also has some coefficient in front that you can compute from the flow of the RG, and the result is that the combination goes to a constant. It's independent of alpha. And the only dependence on n is here, so if you multiply by n minus 1, it's really a super universal number. All right, we can do more than that. We can really study how the G, the coupling constant, really flows logarithmically to G equals 0. And to do that, what you can do, I will use a method which was introduced by Lucia, Weiss, and Ole Wolf. You can, first of all, define a renormalized effective coupling constant for the model by exploiting the RG invariant quantity. So you can see that from the lowest order in G, if you start from the nonlinear sigma model action, you find that in the lowest order G, for example, psi over L is apart from factor n 1 over G, and same goes for the stiffness. And this suggests that you can really define and take as a coupling constant this right combination of the spin stiffness or of the psi over L constant. And now to start, you can, using the method of Lucia, Weiss, and Wolf, you can determine the coefficient of the beta function by considering the so-called step scaling function, where you compare essentially how this effective G changes when you scale L to SL We take s equal 2, for example. And then you can show that if the beta function has this expansion, where I introduce, okay, so here there is a missing exponent, this was alpha g squared, plus the next term, then this scaling function as a function of g now, not as a function of L, but as a function of g, display this Taylor expansion, where we have a trivial linear behavior that we can also subtract directly since it's not particularly interesting. And the next term contains in the prefactor of g squared and g cube the alpha and also the next to leading term in the beta function. And so this is a very clear recipe to determine the coefficient of the beta function. This left-hand side we can compute with Monte Carlo simulation. Then we do a Taylor fit of the Taylor expansion, and we get these two parameters, alpha and b. So this is more precise than just fitting the linear behavior of the various RG invariant, because there we have subleading logarithmic term. Here we are really looking directly at the expansion of the beta function. And right, so this is an example of the calculation I show you. So I take this step function and subtract already the trivial linear behavior. And you see that in the case of the G defined in terms of the spin stiffness, there is the various data for various value of the coupling constant and various lattice. They tend to nicely align on a single curve. In the case of Xi over L, we see much more scaling corrections. In particular, the points which for each group of colors, the points which are on the right are the ones which correspond to the smaller lattice sizes. So clearly, for example, these points which seems to be completely off are the ones with smaller lattice sizes, suggesting that here the scaling corrections are more important. And it also, this plot shows how the cubic term is relevant for the data we have. Because if here the solid line is this right-hand side truncated to the second order and use the value of alpha that I know from the normal unistatic class. And of course, close to g equals 0, the solid curve is still have a relatively good match with the Monte Carlo data, but then you see that the cubic term is really relevant here. And then by doing a suitable fits, then you are able also to extract an estimate of this coefficient b, which is the next to leading term in the beta function. Same goes also for the case of the plane defect. Also, here we observe that actually the correction to the simple g squared term are more important. What you find in summary is that in this way you are able to extract the value of alpha, which now matches. Before there was some small deviation from the normal unistatic class. Now matches the results I know from the normal unistatic class. We also find, in all cases, a fitted value of the next term, which is negative. And this has clearly implication on the value that you can observe. Because if you have a finite range of sizes, you can think, see, the beta function, I write it as sort of effective alpha, which is my alpha plus the correction term b. And when you simulate a model on a finite range of sizes, likely you observe an effective value of alpha that describes the effective logarithmic scaling of the various RG invariant quantities, which has some small correction, b times g. And if this correction is negative, and in all cases negative, then effectively you will, for a given range of size that you can reasonably simulate, observe a small bias, a small negative bias in alpha. And that's exactly what we observed before. Particularly, this b seems to be larger in the case of the depending on well, you know, for the parameter that we are able here to fit the b correction were more important numerically. Also, this correction, effective correction you see, depends on the value of the coupling constant, because the stronger the coupling constant on the boundary, in a sense, you are starting the RG flow from a value of g which is closer to g equals 0. So that means that if you do Monte Carlo simulation with a stronger value of surface coupling, you will see less deviation from the true alpha value. Okay. Another interesting observation is that okay, we have for n equal 2 and 3 for open boundaries, we have that b is negative. There's no sign that the b becomes smaller and smaller. So if b remains negative, in the moment when alpha changes sign, there are no other zero in the beta function, and that means that simply when alpha becomes negative, we just have the ordinary universality class and no other universality classes. All right, so that brings me to a summary. There has been quite some advancement in the classical standard model problem of a 3D ON model in the presence of a surface or also on a defect, two-dimensional defects, which led to the discovery of this new extraordinary log phase. I showed you that Monte Carlo simulation indeed confirms the existence also for n equals 3. Using the theory prediction that the extraordinary log features are characterized by some boundary operator product expansion of the normal universality class, we have been able to extract this parameter alpha. And one of the striking features of this extraordinary log phase in Monte Carlo simulation is the presence of this logarithmic finite scaling, which is rather peculiar. And using this logarithmic finite scaling, we have been also able to compute the lowest coefficient of the beta function, and they match then the expected prediction coming from the normal universality class. And we're also able to understand where the effective correction arises from. With that, I leave you with a few references of the work I've presented today. And the last one is a bit still a work in progress, but hopefully will come out soon. And with that, I thank you for your attention.
So for the case of plane defect,
Yep.
and do you get like two decoupled surface? Can I say they're two decoupled surface, or they are actually coupled for the extraordinary log phase?
You mean in the simulation? No, in the
No,
simulation?
I mean numerically, what do you observe, right? Sometimes you know that the surface defect indeed will just become
The
two
surface or the plane defect?
The plane defect will just become two decoupled surface defect.
Yes, in the ordinary case. That's exactly the ordinary case. When the beta is small, the coupling is smaller than the bulk one, then it flows away and it goes to the ordinary. So it flows to zero essentially, so you have an ordinary universality class.
And then for the extraordinary, what happens?
And for the extraordinary one, that's so you flow logarithmically slow to the order phase. So that's why you have all these logs. It's the same. It's qualitatively similar to the case of a boundary, a true surface, that except that the alpha parameter is different and it's always positive.
So let's say the system above the plane defect and below the plane defect just decoupled. Can I?
No, I won't say that it's decoupled, because if it were decoupled, then you had just the ordinary universality class. I think that the logarithmic flow.
Yeah, I can understand. For n above nc, then they will coupled, right? But what about n equals 2 and 3?
So if the plane defect were decoupled, no, then you have a nonlinear sigma model with ON, and it's always disordered for 3 or 4. No? But now this is coupled really to the bulk. And the coupling to the bulk enters in the beta function, enters in this coefficient alpha. That's where the coupling to the bulk, the critical bulk, comes. And it makes the surface to slowly flow logarithmically.
Probably you don't understand what I mean. Yeah. Yeah.
Like the deep IR, it seems like the upper half volume and lower half volume will get decoupled.
So maybe we can discuss later.
For the normal universality class,
Yeah.
if you apply a symmetry breaking field on the plane defect, that indeed cuts
Yeah.
top half and the bottom.
But it won't be the case for the extraordinary log, right?
Well, now they're both kind of coupled to this nonlinear sigma model on the defect, so you probably have that almost decoupled, but with kind of log corrections.
I see.
Probably the coupling goes as one of the modes.
I see. Okay. Yeah. Thanks.
So if you have a ordering field, that's what you call the normal boundary. So that's the Dirichlet boundary condition. But if no,
no, fixed, yeah.
Well, fixed is the same as zero in terms. There's no fluctuation, right? There fluctuation.
No.
There's
Symmetric. And fixed normal is fixed symmetry break.
Oh, I see. The order parameter vanishes versus you pick the orientation. I see. But is there, on the other side where it's ordinary, is there any modification to the bulk critical phenomena as you approach the surface? Like, is it affected by, are the correlations along the surface where you have surface is not ordered in the ordinary case, are those correlations different in the bulk and the surface?
In the ordinary, yes, they are definitely different. Yes.
Okay, so that delta, so it's some power law, but the delta is different.
Yes, and the ordinary is definitely much larger, so they decay much faster. And you can imagine that they have less nearest neighbor around.
Yeah,
so
there's no second
they
point.
decay much faster, the correlations.
Okay, thanks.
Yeah, I wonder the boundary critical theory of phase transition can be studied by integrating all the bulk. Then you have effective boundary theory with algebraic interaction, which is not renormalized. Whether, this for both speakers, whether this can be a way to study this boundary system without doing the bulk.
But the bulk is an interacting field theory, so it's not just a Gaussian model you can integrate easily. So I don't know how you do it.
Probably, but the point is following is whether one can assume the one can simulate the boundary transition by designing a boundary theory without bulk. But the boundary theory have some, putting by hand some kind of algebraic long-range interaction. And when you tune this power and the strength to a certain degree, that can completely simulate the bulk effect. Then you just do the boundary, non-local boundary theory, reproduce this the boundary phase diagram and the boundary critical behavior, things like that. I just wonder whether this boundary critical theory can be understood as a field theory, but allow algebraic long-range interaction, then you can get this boundary phenomena. Whether that picture is okay, or the bulk effect is more non-trivial.
So maybe you know better. No,
Maybe I can try to answer. So I think the answer is no. And one way to see it is, for instance, when your boundary field theory, right, when it sits on the boundary of a critical bulk, you know that there are going to be these protected operators, like the displacement operator that always has dimension 3. And if you have some just two-dimensional model with long-range interaction, it's very kind of unnatural to get this protected operator. And same with the tilt, for instance. So from the point of view, if you think about the correlation functions, they on the boundary, say 4-point functions and so forth, they satisfy the usual crossing equation. So you can think about it as a two-dimensional conformal field theory, but this two-dimensional conformal field theory has some special protected operators, and actually how to put that into the bootstrap, that it comes from some critical bulk rather than some critical local bulk than just some two-dimensional theory with some. Also, the other issue is that the power law interactions that you are going to get is not going to be just 2-spin, right, but like 4-spin and 6-spin, and so that's the.
So maybe the answer is following. So let's push it again. I suppose I always integrate the bulk to produce some long-range interaction on the boundary to simulate the bulk. But however, the problem is that maybe this algebraic interaction couple many different operators.
Yeah,
it's not
absolutely.
just other parameters.
Absolutely, yes.
All other So actually, you have introduced maybe infinite number of algebraic interaction, and then you can simulate. But that be maybe too much. It's worse than just doing bulk. Okay.
Yes.
So there's a complementary problem that I've looked at for a few years, where rather than looking at the critical theory, you look at the ordered phase. You look at the Goldstone modes, and you study quench disorder, let's say, that only lives on the surface. So in those theories, it is very productive to integrate the bulk out, and now you get some very long-range interaction kind of exchanges on the surface, competing with quench disorder, let's say. And so you get all kinds of modified functional RG, like understanding of how disorder affects this long-range interacting surface. So that's very productive, but not at the critical point in the order phase.
Okay, I think we are out of time, so let's thank the speaker again.